All right, 5.4, last section is chapter 5, fundamental theorem of calculus. There's actually two fundamental theorems of calculus, and we're kind of doing it in reverse order. This one, the second fundamental theorem of calculus, it's not so much that you have to memorize this is the second fundamental theorem of calculus, but when I say this is a fundamental theorem of calculus, you should recognize this, okay? And this we kind of know, but we're going to see it in a different way later when we're talking about it. So for this one, we know, oh, we take the antiderivative, we plug in b, and then we plug in a, and then we subtract them. That's how I get the integral from a to b of this function. I have to take the antiderivative. Okay, so we know this, but this is written in a certain way where like later we're going to solve some problems. So I'm going to be like, oh, remember the second fundamental theorem of calculus? I'm going to write it and we're going to use this fact, okay? So what we're really going to get to though for today, well, and tomorrow and this week, is in regards to particle motion. So we're going to talk about two things. So we know for particle motion, the derivative of position is velocity. So let's say you have this velocity graph. Okay, so right here I have a velocity graph, okay? So here, I'm going to label it. So this is v of t. So here's my velocity graph. And then my velocity graph is some sort of like x cubed, right? I can tell it goes up, it goes down, it goes back up. So it's some sort of x cubed, or maybe it's an x to the fourth and I just didn't draw the rest. But it goes over the x-axis above and then it goes below. So if we look at this, we see two areas going on between A and B. We see this positive area and we see this negative area. So I don't know if we've talked about positive. Oh, we have. Okay, so we see this positive and this negative area. We also know this is like when you go to the right, this is when you go to the left. Or this is when you go up, the particle goes up this much and it goes down that much. So if I were to ask you from A to B, you know, if I start at A and end at B, is my particle going to be to the right or the left of the origin? Well, I would say to the right, because there's more right movement than left, right? There's more positive movement than negative movement. If I said, is it, you know, above or below the origin, you'd be like, oh, it's above, because there's more positive. Okay, so there's two new words that we're going to talk about, displacement versus total distance traveled. So before we take a look at this, which I know you already wrote, but before we take a look at that, I want to show you my little picture example, okay? So the difference between displacement versus total distance traveled. So let's say I live here and you live here, and Starbucks is 3 miles away from you. So if I go in a straight line, okay, so on a street, on just like one street, you go back and forth, left and right, you're 2 miles away from me, and then I can keep going at Starbucks and then come back to your house and come back to my house. Okay, so from me to you, if I go to Starbucks and then go to your house with some drinks, my displacement from me to you is 2 miles. That's how much I've been displaced. So like I start here, I end up 2 miles away from where I started. That is displacement, okay? So you just like do everything and see where you end up. The total distance traveled is different, right? So if you're in your car, you have an odometer. So the odometer tells you how far you've gotten, how many miles. So you haven't just traveled 2 miles. No, that's your displacement. That's how far you are from the very beginning of your trip. Instead, you've traveled 2 miles and then another 3 miles and then another 3 miles back. So your total distance traveled, well, mine, if I go all the way to Starbucks and back to your house, is going to be 2 plus 3 plus 3, which is 8 miles. So my displacement from me to you is 2 miles, but my total distance traveled is 8 miles because it's 5 plus another 3. So total distance traveled is when you take all of those areas and you basically make them positive. You just make everything positive. So total distance traveled from me to Starbucks is obviously 5 miles. But like I said, if I go to Starbucks and then back home, what's my displacement? It's going to be 0. I am at the same place where I started. But what's my total distance traveled if I go back home? It's 10 miles. I still traveled 10 miles in my car, okay? I use my car for 10 miles, basically. That's total distance traveled versus displacement. So for displacement, you just find the derivative, or sorry, you find the antiderivative. But for total distance traveled, you're basically finding all the positive areas. So it's like we're taking this and we're bouncing it up, right? Because when you take the absolute value of a function, we're taking all the negative, everything under the x-axis, and we bounce it up, and that gives us speed. So basically, we're taking the antiderivative of speed instead of velocity to get our total distance traveled. So that's why this is area 1 minus area 2, because technically that's a negative. And then this is area 1 plus area 2. So if we found this area, which is like, I don't know, 4, and we found this area, which is like 1, then we'd add them together and get 5 as our total distance traveled. But for displacement, it'd be like 4 minus 1, which is 3. Okay? So that's the difference. Okay. So then hopefully these make a little bit more sense now when you were copying them the first time around. And I want to show you, so displacement, you just find the antiderivative, and I didn't do all the work for it, but I want to show you actually, I know that you can find the antiderivative and you can go ahead and plug in 5 and plug in 1 and then get like a radical, not a radical, sorry, a fraction, right? So I want to show you actually on a calculator. So on a calculator, you are able to do this pretty quickly. So you're going to go to your y equals, so clear your calculator first, obviously, 2nd plus 712, and then you're going to go to y equals, and you're going to plug in the function. So this says t squared minus t minus 12. So I plugged in x squared minus x minus 12, because there's no t here. We can't use t, okay? And then I quit, so second mode takes me back to here. So I'm going to find my antiderivative. We know that that is math 9. I'm going from 1 to 5, and then I go ahead and plug in. So I don't want to plug this in because I already have it in my calculator. There's 2 ways to find it. Are you ready? So the 2 ways to find it, the first way, y is a variable, okay? So I can go to vars, which is variables. I can go to the right where it says y variables, and then function, I press enter, and then I want my y sub 1 that I already put into my calculator in the very beginning. And then this is in terms of x. So that's one way I can do it. I'm going to show you another way that I can go ahead and find that y sub 1. Another way is alpha, that green button, and then F4. So alpha F4 takes you to y variables. It's like a shortcut for the y variables, and then you just press enter. Okay, so I press enter, and then I get negative. See, that's how I got the answer right there. Okay, so you can do this by hand, yes, but then also I want to show you can do this on the calculator as well. All right, sometimes I'll ask you to do it on the calculator. I'll be like, I don't care, and sometimes I'll ask you to do it by hand. Okay, so this one is a little bit different. This says, what's the total distance traveled? To get the total distance traveled, you're going to need to either draw a picture so you know where to split up your antiderivative. So you have to go from A to here, and then from here to B to split up your antiderivative. Or, instead of drawing a picture, I can go ahead and take my velocity, set it equal to 0, and solve for where my time equals 0. So this, based on my velocity, tells me before -3, you're positive, you're above the x-axis, and then between -3 and 4, you're below the x-axis, and then between 4 and infinity, you're above the x-axis. So really, if I'm going from 1 to 5, I only have to care about this. So first, I'm negative, and then I'm positive. So first, I'm under the x-axis, and then I'm above the x-axis. So I can do this 2 ways. So I can put this into a calculator like that. So I'll show you, okay? So I can just say, okay, now just take the positive version of the velocity, and that'll give me an answer. Or if I do it by hand, if I had to do this by hand, I would have to separate and be like, okay, so I separate from 1 to 4, and then from 4 to 5. Well, from 4 to 5, I just find my area, I'm all good. But from 1 to 4, my area is going to be negative. So how do I negate that negative? I put a negative in front, right? Because a negative becomes a positive. So then now this, like, negative area that's between 1 and 4 becomes positive because I negated it. And then I get a positive plus a positive, and then I get this number that's definitely bigger. Okay, so here's how we can do it on here. So I'm going to, again, go math 9. I want to go from 1 to 5, And then I want to do the absolute value. So absolute value is math. And then you're going to scroll to the right and you see absolute. You're going to press enter. And then now I'm going to plug in my y sub 1. So alpha f4, enter. And then I tell it in terms of x. So it's the same thing, but now this part is an absolute value. And that's going to be different if you make the whole thing an absolute value. Because if you make the whole thing an absolute value, that just gives you a positive 18. That's not the same. Okay, so what we really want is we want to bounce that graph above. So if we look at this graph, by the way, so I had that in there already, right? If I were to graph it, I'm going to show you what that, see, so it's positive, and then it's negative down here, and then it's positive. So if I want to find, I'm going to show you one more thing. So I want to calculate, I want to calculate the integral, number 7, between my lower limit, which is 1, and my upper limit, which is 5, okay? So lower limit is 1, upper limit is 5. So this is my negative 18, right? So this is my negative 18. That's why it's negative, because there's so much more negative area than positive. But then how come this is going to be positive? Because this negative part gets bounced up here. It basically looks like a W kind of, and then it's going to have a positive area and then a little bit more positive area. That's how come this is going to be a 26. Okay? Okay. So I think the other parts are more like straightforward. Because water flows out of a hose at a rate of, okay, this is a rate for 2 reasons. 1, it tells you it's a rate, and 2, it says liters per minute, so you know it's a rate. Okay, so even if it didn't say rate, you should know this is a rate because it says liters per minute. How much total water, anytime you're finding the total amount of things, you're taking that derivative, which is a rate, you're taking that rate and finding the antiderivative. So it says the first 18 minutes, that's from 0 to 18. So then you find the antiderivative, and then it's a negative 144, but that makes sense because water is flowing out of that hose for 18 minutes. So 144 positive, that many liters flows out for the first 18 minutes. Okay, we'll deal with this one after number 5, okay? So the first fundamental theorem of calculus is if you were to take, so it kind of makes sense, but I know it looks a little weird. If you were to take the derivative of an antiderivative, so listen, a derivative of an antiderivative, what you should end up getting is the original. The only problem is that when you take the derivative of an antiderivative, you have to make sure that, okay, this is actually, I need to finish this, minus f of x times a prime. Actually, that's finished. Okay, so let's keep copying that. Okay, so technically, I have to do, this is very similar to this, right? So when you find the antiderivative, you have to like plug in b minus plug in a. So same thing here. So you're basically, if it's the derivative of an antiderivative, then it's just going to be the original times, and then what you do is you plug in that times the derivative of whatever that is, and then minus, you plug in the a. Oh no, where's my whiteout? Ah, sorry. This is an a. This is an a. That is an a. There we go. F of a, and then times the derivative of a. Okay, that's a times, not a minus. Okay, so I'll show you what I mean. So here's one example. So for this example, so you're taking the derivative of an antiderivative. So really, I plug that x squared into where I see t, and then times the derivative of x squared is 2x, and then technically minus, and then I plug in a 0, and then times the derivative of 0 is 0. So then really it's minus 0. So that's why I didn't write the second part, that blue part. Okay, so final answer. Okay, same thing with the other one. So if I am finding the derivative of an antiderivative, I'm going to plug this in, and I get sine of 3x times the derivative of 3x minus sine of 0 times the derivative of 0. But the derivative of 0 is 0, so then I don't worry about that second one. So I just set this part minus 0, so it's just that. Okay? Okay, so the next part is, all right, let's talk about average value. But first, let's talk about the actual area of a rectangle. So if we were to take this area between A and B, so if we were to shade this in all the way here as well, okay? If that was sand, and if there was sand underneath that function, okay? And then if I could take that sand, and if I could take my pen or, whatever, and then I could smush that sand down to make it so that it was flat. Okay, so right now the sand would go curved, but if I could smush it down so that it's flat, it would stop at a certain place, right? So that place, I'm going to call C. So this is A, B, and then C is somewhere in between. I'm going to call it C. And then this height is f of C. All right, so this is f of A, this is f of B, this is f of C, right? So I don't know what that height is, but I'm going to call that C. Okay, the area of a rectangle we know, so if that makes a rectangle, that's base times height. What is the base? The base is B minus A, right? So that's the base of this rectangle. What is the height? The height we're calling f of C. So really it's just like f of x. I don't know what the x is, but I'm going to call it f of x. Okay, so what is this really? Well, this, how do you find an area also? So this is like base times height, right? Base times height. But then also, how do you find an area of from A to B? Oh, that's when we take the antiderivative of f of x, and then we plug in b and plug in a, right? So these should be equivalent. So how can I solve for f of c? F of c is what we're calling the average value. So the average value, the average y value, technically, between a and b. What is the average between a and b? We're saying is f of c. So if we set this equal to this, how do we solve for f of c? We're going to divide this to the other side. So that's why that's the average value theorem. Because we took this, set it equal to this, and then we divided by b minus a. So see, when you divide, it's like multiplying by, 1 over, right? So this is the average value theorem. The average value is talking about literally the average value of the function. Okay, so let's say you have this function, and we want the average value from -1 to 2. So the average value from -1 to 2 is going to be, I'm going to go ahead and use the formula, I plug it in, and then I calculate it, and I get 7. What does that 7 represent? 7 is the average y value between x equals -1 and x equals 2. So between -1 and 2, the average y value, this is like our average value, is going to be 7. So if this was -1 and this was +2, this would be 7 as the height. So my average height basically is 7. Okay, going back to this one, what is the average amount? Average is average value. So what is the average amount of water, it goes with this problem, that flows out every minute? So this is the total amount of water after 18 minutes. What is the average per minute? Well, that makes sense that I would take the total and divide it by however many minutes, and that would be 8 liters. That is what you would do here too, right? Because how did you get 144? That was the total. That's when you take the antiderivative. And then why would you divide by 18? Well, it's 18 minus 0. And then if you do 18 minus 0, isn't that this formula? So that's why the average amount of water is like the average value of the water every minute is going to be this divided by 18 minus 0 technically, which is that divided by 18, which is 8 liters. And that's the average per minute. So 8 liters every minute is the average amount of water. Okay, so your homework is, keep these in mind because they, happen in the homework at some point. And then your homework is a lot of review. So this is a lot of review, but then this is a little bit extra. So I'll give you answers for A through E. I'll probably just post them today, okay? And then for this one and this one, feel free to, that I'm not going to tell you what to do. Actually, yeah, I'm not going to tell you what to do. I'll give you the answers though, okay? I'll post the answers. Okay, good luck. I will see you tomorrow.